Good day. So, our topic for today is QoS and multimedia, that is quality of service and multimedia. So, we will just look at these one by one. Quality of service. Now, what is quality of service? QoS refers to traffic control mechanisms that seek to either differentiate performance based on application or network operator requirements, or provide predictable or guaranteed performance to applications, sessions, or traffic aggregates. Well, it talks about a lot of things. The basic notion is this, that there are some applications which require one kind of quality of service. By the way, the quality of service may mean so many different things, but the most important of them are the delay, network delay, and the packet loss. All right, delay and various ways the delay. Now, these two parameters, and it may sort of come in various ways, they affect differently when you talk about different applications. And multimedia, by multimedia we mean audio, video, etc. I mean put on the going through the net. So, that has got a different kind of QoS characteristics, that has got a different set of requirements than, let us say, a file transfer. So, we will see how we can get a handle on this QoS and how multimedia traffic is handled in the network. And sometimes it may so happen that some applications are more important than others. So, they need a better guarantee of performance. So, such things also come under quality of service. Just take examples, video and audio conference, they require bounded delay and loss rate. Okay. That means the delay has to be bounded, and also the variability of the delay should also be within bounds, and the loss rate of packets, that should again be bounded. All right. As you can see that this is quite different from let us say a file transfer, where the losses loss of some packets cannot be tolerated at all. So, it is somewhat tolerant of losses, but more sensitive about delays, and but you know, in a when you are downloading a file, you are usually not that sensitive to delays. Video and audio streaming, that means maybe some from video server or some internet radio, etc. audio or video is being streamed to different clients. So, this again requires a bounded packet loss rate. Delay, it may not be so sensitive to delay, why we will see later. There may be some time critical applications like real time control. Here again bounded delay is important. Then there are some valuable or so called premium applications. Maybe the those who run these premium applications, they are ready to pay more for these, and they expect better guaranteed service than, let us say, less premium or less valuable applications. QoS requirements can be specified as delay variation jitter, throughput, that is what is the rate at which you can send data, and error rate. Error rate means some packets getting lost and things like that. Now, there are two approaches to this, stateless and stateful QoS solutions. Now, stateless solutions, router maintain no fine grained state about traffic. This has got a positive point, that this is very scalable. Actually, the kind of thing that we have talked about till now, that routers do not maintain any states. Sorry. So, the routers do not maintain any states. So, it is simply the raw packet forwarding capacity that comes into the question. So, this is that way very scalable, this is also quite robust, but it has weak services, because there is no guarantee about the kind of delay or performance that a particular application will have to encounter. On the other hand, we have stateful solutions. Routers maintain per flow state. Now, so this flow is very important while guaranteeing a quality of service. Suppose there is some audio conferencing going on between some people. Well, it may be the audio signal naturally is digitized and packetized, and then these packets are flowing. This is a packet switch network. Essentially, at the heart of it, it's a packet switch network. But at the same time, we not only talk about a single packet by an entity in itself, which is how we have dealt with packets so far, but the end users are interested in the flow. That means the flow of packets. So, all these streams of packets that are flowing which contain this audio signal, they constitute a flow, and the users are actually interested in the flow. Suppose somebody wants some guarantee on this service, he wants a guarantee on the service of this flow. So, merely looking at packets is not enough, but if that is not enough, you have to go from a purely stateless situation to a stateful situation. So, and actually you have to sort of make out that this is a part of a particular flow. So, naturally if you are stateful, that means if you go into the packet and look at what the kind of packet it is and maintain a state about it in the router, then you can give powerful services like guaranteed services plus source utilization. Now, fine grained differentiation between different flows, you can give protection, the problem that this is much less scalable. That means when the number of flows through a router starts increasing, and that is what will happen in any of the core routers, then the core router would not be able to handle this. So, it is much less scalable and much less robust. But we will look at both these things, both the approaches, and the first one is a fully, I mean it is a stateful system, and this is known as integrated services or INTSERV. So, this is an INTSERV architecture or ISA. It is an architecture for providing QoS guarantees in IP networks for individual application sessions. So, we are talking about the entire session and the flow that has gone on during that session, so a flow consisting of so many packets. It relies on resource reservation and routers need to maintain state information of allocated resources, for example, G, and respond to new call setup requests. So, the point is in this situation, I mean how will you guarantee that this particular flow which is starting will get the requisite kind of guarantee of service, that means its delay would be bounded, etc., etc. For this you have to specially reserve resources at the intermediate points, I mean resources like buffers, with resources like CPU time and so on. So, if you are doing so, you have to reserve this resource for this particular flow so long as this flow continues. That is how you would give a better service to this particular flow than to any ordinary packet. So, it will have to maintain the state in the form of these reservations and respond to new call setup requests. For example, as soon as you take out some resources, naturally it goes out of the available resource pool, and so if the new call setup request comes for another session, some intermediate router may not be able to handle that. So, it will not be admitted. So, network decides whether to admit or deny a new call setup request. So, this is the basic idea of INTSERV. So, in this case, since you have to reserve resources, there is a call setup phase, just like so this is almost like a virtual circuit which is being set up. So, there is a call setup request which goes from the source to the destination and back, and on the way it reserves resources at each of the intermediate nodes, and if each of the intermediate nodes, that means each of the intermediate routers are ready to provide these resources, then the call will be admitted. For resource reservation, there is a particular protocol called this reservation protocol or RSVP. So, this constitutes of call setup and signaling. Then there is a traffic QoS declaration and per element admission control, that means whether the call could be admitted or not. Then there will be QoS sensitive scheduling, that means when a router, I mean first when a packet arrives, it may go into the buffer of a router and there may be various buffers. Now, each of these packets will have to be scheduled for processing and then forwarding. Now, this processing may not be done in an uniform manner, so it may be done in a QoS sensitive manner. Similarly, routing algorithm, there may also be QoS sensitive routing algorithm, QoS sensitive packet discard strategy. So, all these things come under the in-served QoS components. So, we have talked about scheduling and some of the other things. So, we will talk now about RSVP. So, RSVP, this is internet signaling, it creates and maintains distributed reservation state. This is decoupled from routing. Okay. One thing is to use routing for setting up paths, but then this has to reserve resources. So, this is decoupled from routing. It uses multiple trees set up by routing protocols, not RSVP. So, multicast tree is set up by routing protocols. RSVP is for reserving protocols there, unlike ATM or telephony signaling, where the call, while doing the call setup, you actually assign the virtual circuit. This is initiated by the receiver. This scales for a multicast, and it may use soft state, that means reservation times out unless refreshed. So, you have to I mean refresh your reservation from time to time, and otherwise one particular flow may reserve and never use it. So, that part will go away. So, that is why it will have to sort of go out of the reservation, will have to time out. And latest paths discovered through path message, forward direction, and used by reservation messages in the reverse direction. So, this signaling semantics, you have a setup acknowledgement, setup response, then you have admission control, tentative resource reservation and confirmation, and this can be done in both directions, simplex and duplex setup and no multicast support. These are the signaling semantics in brief. So, let us look at how this goes. Suppose this is the source. The source would initiate a setup. So, it will send a setup call to the first switch controller or router, we will go to the another one. Finally, let us say it reaches the destination. Each of the intermediate nodes send a setup ACK, so that the source knows that this is the way it is going to go. The path is being set up, and then setup response will come, and an acknowledgement will go to the destination, and another setup response and acknowledgement, setup response and acknowledgement. What we will have to see is that in this fashion, after this the resource has to be reserved at each of the node for whatever service that is being asked for. So, session must first declare its QoS requirements and characterize the traffic it will send through the network. Okay. So, there are two specifications, RSpec and TSpec. The RSpec defines the QoS being requested, quality of service, that what kind of bound we want on the delay, what kind of bound we want on the jitter, what kind of packet loss is acceptable to me, and depending on this the resource is going to be reserved. That means maybe a special queue or buffer will be set up just for this flow, or maybe something will be done with scheduling, there will be some weight given to it for processor time and so on. in the intermediate node. So, there is a, and then there is a T spec, that is traffic characteristic, that what kind of traffic, what is the burstiness of the traffic, etc., etc. So, such traffic characteristic will also have to be sent. So, depending on the T spec and the R spec, the intermediate nodes will compute what kind of resources this will require. So, a signaling protocol is needed to carry the R spec and T spec to the routers where reservation is required. RSVP is a leading candidate for such signaling protocol. So, far as call admission is concerned, routers will admit calls based on their R spec and T spec, that whether they can handle or they can manage to give so much resources for this, and of course, there are financial side also, that whether the whoever has initiated whether he has an agreement to pay for such premium service, and based on current resources allocated at the routers to other calls. So, if other senders have already reserved full most of the resources in the intermediate routers, then a new call may not be admitted. So, this is a diagram. You see, we have this is the router, the request, it specifies the traffic, the T spec, and the guarantees of service which is required, which is the R spec. Now, this reply to element considers unreserved resources and the required resources for this new request. If it can handle that, then it replies whether or not request can be satisfied. So, this achieves per flow bandwidth and delay guarantees. Example, suppose we want a guarantee 1 Mbps and less than 100 millisecond delay to a flow. So, suppose we have a network like this. First, the receiver will just allocate resources, that means perform per flow admission control. First, of course, the path has to be set up, that has not been shown, and now this is the in the return response path. So, perform per flow admission control. So, install per flow state. So, for this state this flow has to be recognized. So, for that the router has to have a per flow state. Then challenge, maintain per flow state in a consistent manner right up to the sender. If all the routers agree, then only you can give it. And then when sender starts sending, first of all it has to be classified that this is indeed a part of this flow. So, per flow classification is necessary. Then depending on how it has been classified, it will be put in the appropriate buffer, and the corresponding buffer has to be managed. So, per flow buffer management is also necessary, and this way it will go through all the routers. Per flow scheduling is necessary for CPU resources, and the flow will go through. So, in the data path we have per flow classification, per flow buffer management, per flow scheduling, whereas in the control path install and maintain per flow state for data and control paths. So, that has to be done with buffer management. So, you see that for each of the flow the router has to do a lot of work. So, this does not scale, unfortunately. So, this is very good at giving services, but if you are trying to maintain per flow kind of classification and management at each of the nodes, this would not scale, because if the number of flows goes beyond a certain level, then it will be very difficult to maintain it. It will be very difficult to properly give it buffers and queues, etc., in the intermediate node. So, that is why it does not scale so well. Now, stateless solutions are more scalable and they are more robust. Stateful solutions, of course, as we have seen, provide more powerful and flexible services. So, it gives guaranteed services plus high resource utilization. It can make fine grained differentiation between different flows, and it also gives you protection on the way, since you are sort of demarcating each of the flows. Demarcating the flows is somewhat similar either to say setting up ATM virtual circuits. When you do that, you also reserve requests, but that is done while setup call setup itself. That is not done by a separate reservation protocol. Anyway, so it is similar to that, or it may be similar to, let us say, MPLS, where a particular flow is can be differentiated from other flows, and it may be treated specially. Now, then the point is, on the one hand you have the raw internet which just takes a packet by itself and just tries to route it. If it cannot route it, it is the best effort, it goes off, that means it is discarded. That is one end of the spectrum. The other end of the spectrum is that you have a full per flow classification and management for each of the flows, alright. So, where you can have a very good control, etc., but it does not scale. So, there is a question that can we do something in between, alright, and that is where the next model comes, which is known as DiffServ, differentiated service. So, here also this is also stateful, but here each flow, each distinct flow does not necessarily mean a distinct state, alright. So, these are sort of short state which can include a number of which you can accommodate a number of flows together, so that the pressure on the routers in the intermediate nodes or in the backbone of the network becomes less. So, scalability, maintaining states by routers in high speed networks is difficult due to the very large number of flows. So, DiffServ provides reduced state services, that is, maintain state only for larger granular flows rather than end to end flows, tries to achieve the best of both worlds. So, DiffServ is intended to address the following difficulties with IntServ and RSVP. Flexible service model, IntServ has only two classes, one to provide more qualitative service classes, one to provide relative service distinction like platinum, gold, silver, etc., and simpler signaling than RSVP. Many applications and users may only want to specify a more qualitative notion of service rather than a quantitative notion in the previous case. So, this is a DiffServ model. You have an ingress edge router and you have the interior routers, it goes to the egress edge router. So, edge routers, traffic conditioning, that means policing, marking, dropping, etc., they are done at the edge. The reason we want to do them at the edge of the network is that there the number of flows, etc., is much lower. So, you can handle it over there. And when you come to the core routers are very busy. So, there we do not want to do that over there. So, set values in DS byte in IP header based on negotiated services and observed traffic. Interior routers, traffic classification looking at this byte and forwarding near stateless code. Okay. This is almost like let us say MPLS or ATM. Okay. Use DS bytes as index into the forwarding table. So, edge router, it does per flow traffic management, marks packets as in profile or out profile. Core router, it does per class TM, buffering and scheduling based on marking at edge. So, marking has been done at the edge. Preference is given to in profile packets, that means in profile means that some traffic shape has been has been negotiated or is expected, and then something comes which is out of that shape. That means somebody is sending maybe more packets than are more packets per unit time than was negotiated. So, those are out of profile packets, and assured forwarding. So, this is what the core router does. If you look at this, so marking and per flow classification, etc., is done at the edge, but in between the scheduling is done. The packet is marked with the type of service in IPv4 and traffic class in IPv6, renamed as DS. 6 bits used for differentiated service code point DSCP and determine the PHB or per hop behavior that the packet will receive. 2 bits are currently unused. So, 6 bits for this differentiated service code, and this service code will sort of dictate how this particular packet will be treated. For forwarding, per hop behavior or PHB carried out in the interior routers, It's simplified process based on class and resource specified when SLA was created. So, PHB has been defined in a certain RFP. For example, let us say you may, so it may have this things for premium service, it should have low loss, low delay, low jitter, assigned bandwidth is equivalent to point leased line. So, that is the kind of service we want, although this is not leased, this is the plain packet switch network. Guaranteed through policing and shaping in order to stay within the departure rate of leaky bucket and WFQ. So, that is how it is guaranteed, and then since all the intermediate nodes guarantee that, so it will get premium service. Traffic conditioning. It may be desirable to limit traffic injection rate of some class. Users declares traffic profile, e.g. rate and bus size. Traffic is metered and shaped if non-conforming. So, we have seen this already when we discussed congestion control. So, the packets are classified and then they are marked. Now, when they are classified and marked, naturally for the session some kind of T spec, that is traffic spec has been was already negotiated. So, it meters to see whether it conforms or not, and then the traffic may be shaped if by chance some burst comes, and if the system can handle it, then it will maybe keep it for some time and then forward it only at an appropriate rate, but if it goes too much two-way out, then it drops it here itself. Now, we will discuss how multimedia, this QoS of course is absolutely important for especially for multimedia traffic, as was explained. For ordinary data traffic like web traffic or FTP, file download, etc., those usually are not very sensitive to delay, and of course variation in the delay, that means you may get a lot of packets in one bunch, then packets may be slow in coming, etc. Now, these things really do not matter, at least they do not matter much if it is within some bounds. But in multimedia these things are very important. For example, when we talk, if the delay is beyond a certain level, then we feel very odd. Okay. For example, even a few years back, if you had made an international call which is routed in a very peculiar way, you would find a lot of delay when you are speaking, let us say, to somebody in USA. Okay, that is quite annoying. What is also, additionally what is annoying is that if the delay remains constant, somehow people can manage it, but if the delay keeps varying a lot, that is, if there is a lot of jitter, then that is very irritating for people. All right. So, the multimedia stream has on the other hand, unlike data, let us say when we are talking, maybe a few bits are dropped here and there, it will not matter too much. Maybe if you analyze it using machines, you will find some difference in quality, but as such in the human to human perception, most of the time it does not matter too much. So, the multimedia traffic is quite different from, let us say, ordinary data traffic, and as network is spreading and because of the way it is growing, people find it cheaper and most convenient to use this internet or use this computer network for this what was traditionally telecoms domain, in the sense for audio or video conferencing. People are using it. So, and also the trouble is that many of the routers, etc., we have talked about INSERV, DIFSERV, RSVP, etc., but many of the routers on the way are not going to support this, all right, because you need a consistent support throughout the path. So, people still use the, maybe people still try to use the raw internet, which is just handling it at the packet level, not really taking note of the flows, and still try to handle multimedia. So, how for that a set of protocols has evolved, and we will just look at those protocols now. So, principles: classify multimedia applications, identify the network services that the applications need. Then making the best of best effort service, that means you have a best effort service. So, how can you make the best of it, that we will see in RTP etc., and mechanism for providing some QoS. So, these are specific protocols for best effort and architectures for QoS. Of course, if the network at the network level, if you had supported QoS, these would have gone through much better. There are various classes of applications and not all are the same. There is streaming of stored audio and video, that is one kind of application. For example, you download a song or a movie maybe. So, that is a streaming or stored audio and video is being streamed. Then there is streaming of live audio and video. Then of course, there are real time interactive audio and video. So, this way you can classify. By multimedia application we mostly mean audio and video. So, this way they can be classified. So, fundamental characteristics, as we have already mentioned, that they are typically delay sensitive. So, they are sensitive to end-to-end delay. They are also sensitive to delay jitter, which is the variation in delay. They are loss tolerant. So, infrequent losses cause minor glitches. So, this is the antithesis of data which are loss intolerant, but delay tolerant. Then sometimes we like VCR like functionality. When suppose we are seeing a video, so video we tend to sort of equate it with the kind of functionality that we get in a VCR. So, client can pause, rewind, fast forward, push slider bar, etc., etc. And at the same time, let us say when it starts a multimedia session, maybe an initial delay of maybe 5 to 10 seconds is okay. 1 to 10 seconds until command effect, that also seems to be okay. So, do we need a separate control protocol? We do, because we really have no other way of getting any kind of control feedback etc. on these streams, as we will see. So, timing constraint for still to be transmitted data in time for play out, all right. So, we will look at this. Suppose, so we have, let us say, streaming of stored multimedia. Suppose this is the recorded video which is being sent, all right. So, this is the recorded video, this is the cumulative data that has been sent. So, this is like a staircase, because they are being sent as packets. So, chunks of data is going together, so they are being sent. And then first of all you record the video and the video is sent, and in the third position the video is received and played at the client. So, this is streaming of stored multimedia. There is of course a network delay between the when the video is sent and when the video is received. So, as soon as you send it, you cannot start seeing it immediately. So, streaming, at this time client playing out clearly part of video while server still sending latter part of video. So, maybe he has in this particular diagram the client has already started seeing something, although some of the data has still not been sent. Now, this is streaming of stored multimedia is different from streaming of live multimedia. For example, say internet radio talk show, that is a live multimedia, live sporting event which is being webcast. Now, streaming has a playback buffer. So, playback can lag tens of seconds after transmission, but it still have some timing constraint. Interactivity is limited. For example, obviously, if it is live, you cannot fast forward it, but rewind and pause may be possible. All right. So, it depends on how you are handling it. So, this is unlike a stored multimedia, where fast forward would also be possible. An interactive real time multimedia, So, this is one of the most important ones, applications like IP telephony, video conference over the web, distributed interactive worlds, etc. So, these are applications of interactive real time multimedia, which of course has the most stringent QoS requirements. Say end to end delay requirements, different applications have different kinds of requirements. For example, if it is audio, if the end to end delay is less than 150 millisecond, it is good. Okay. Less than 400 milliseconds, maybe it is okay. Beyond that, people seem to be bothered a lot. So, it includes application level, that is packetization and the application level delay, and then network delays. So, higher delays are noticeable and they impair the interactivity. Session initialization, how does Collie advertise its IP address, port number, encoding algorithm, etc. Because while making a, I mean, we have taken an example of an audio, let us say like an IP telephone call. So, all these issues are also there. So, which we will discuss towards the end of this lecture. So, if you are using a standard TCP or UDP IP, this is what we would have to do actually, but there are no guarantees on delay or loss. But multimedia application requires some QoS and level of performance to be effective. So, today's internet multimedia applications use application level techniques to mitigate as best as possible. So, this is what we mean by the best of best efforts. So, this is what we, that means we cannot do anything maybe at the network layer, etc. If we could maybe implement an INSERV or DIFSERV, it would be nice, but in many places, most of the places, that is not practical at the moment. So, we do something, we try to do something at the endpoints at the application level. So, application level necessarily means the endpoints, because intermediate, so it will not go right up to the application layer, it will maybe penetrate a little deeper, we will go into that. So, this is mostly done from end to end. So, this is whatever is best is possible, that is what we try to do. So, in this suite of protocols, in this number of protocols, first we look at real time protocols RTP, that is RFC 1889. RTP specifies a packet structure for packets carrying audio and video data. So, RTP packets provide payload type identification, what type of payload it is carrying, packet sequence numbering, time stamping. This time stamping is important for doing giving some feedback, that we will see when we go to the next protocol, RTCP. RTP runs in the end systems. RTP packets are encapsulated in UDP segments. Interoperability, if two internet phones applications run RTP, then they may be able to work together and they may sort of you may talk to each other through the network. Now, RTP runs on top of UDP. This is once again for obvious reasons, we have seen both in TCP and UDP. UDP is a very lightweight protocol, so it is also expected to be much more efficient than TCP. TCP is a heavyweight protocol, so it has a lot of overhead and all these acts of course keep on flowing. So, it uses UDP. So, RTP libraries provide some kind of support over and above the transport layer library. So, that is where that is how RTP runs on UDP, and so this is a provide a transport layer interface that extend UDP. So, port numbers, IP addresses are there in UDP itself, and then payload type identification, packet sequence numbering and time stamping. This is what RTP adds to UDP, and then the application really is here. So, as I said that it moves a little bit into the application domain, maybe just to look at the RTP header to give somewhat better service. RTP by itself does not provide any mechanism to ensure timely delivery of data or provide other quality of service guarantees. It cannot, because that really depends on the what is happening on the way. And RTP is running just between the two endpoints. So, RTP encapsulation is only seen at the end systems, it is not seen by intermediate routers. So, routers providing best effort service do not make any special effort to ensure that RTP packets arrive at the destination in a timely manner, they will not do that. So, the services in between is still best effort. What can we do? Well, since we look at it at the end points, so there we can effect some kind of control. If you have noted that this RTP protocol, this RTP header goes in front of the payload for the data, that means as let us say it is voice which is going. So, as the voice signal is digitized and packetized, before each packet which is produced by your application layer, the RTP header will come. So, it is really in the data. There is a separate control protocol called real time control protocol or RTCP. Now, this is used in conjunction with RTP for multicast transmissions. Now, each participant in RTP session periodically transmits RTCP control packets to all the other participants. Now, each RTCP packet contains sender and or receiver reports. So, report statistics etc. useful to application, and this is what you might use to improve the performance of your session, because nobody else out there in the inside the network, inside the backbone, nobody really knows about your session. So, it is only the endpoints, but they exchange this kind of statistics through the RTCP packets, and then the application can control maybe the rate at which things are being done etc. So, some kind of feedback mechanism is present. So, statistics include number of packets sent, number of packets lost, inter-arrival jitter etc. So, feedback can be used to control performance. Sender may modify its transmission based on feedback. So, this is the main point, that you get some kind of feedback. By the way, this is running on UDP. So, there is no ACK packet coming on which you can send the statistics. So, they have to go. What is done is that this is RTCP is actually in band control. So, a part of the bandwidth is kept for RTCP, and through this bandwidth they exchange this kind of information and the timestamp. So, you know that how much delay is being experienced at the other end, and after having all these statistics, you may do what you can at the application layer to modify the way you are transmitting to get better service. So, there are receiver reports. So, fraction of packets lost, last sequence number, average inter-arrival jitter etc. they are a part of the receiver report. Sender report .SR so, SSRC of the RTP stream, the current time, the number of packets sent and the number of bytes sent. Source description SD, the email address of sender, sender's name, SSRC of associated RTP stream etc. So, provide mapping between SSRC and the user or host name. Another use of RTCP is for synchronization. RTCP can synchronize different media streams within an RTP session. So, consider a video conferencing application for which each sender generates one RTP stream for video and one for audio. Now, the point is you have got two streams of packet, one for the video streams which will sort of go in and then the audio has to be synchronized with it, alright. The sound is coming and the lips are moving in some other way and the sound is coming in some other way, that will not do at all. So, they have to be synchronized. Now, in order to synchronize this, RTCP uses the timestamp which I referred to earlier and tries to synchronize the two different streams. So, that is another important use of RTCP. So, timestamps in the RTP packets tied to the video and audio sampling clocks. They are not tied to the wall clock time. By the way, wall clock times are also exchanged, and this is to get an idea about the delay. Each RTCP sender report packet contains for the most recently generated packet in the associated RTP stream timestamp of the RTP packet, wall clock time for when the packet was created. So, this gives you an idea about the delay. Receivers can use this association to synchronize the playout of audio and video. Then bandwidth scaling. RTCP attempts to limit its traffic to 5% of the session bandwidth. Remember that this is in band control, that means whatever bandwidth is given for the session, so within that only. So, whatever that RTP actual data packets they are using, maybe 5% of that RTCP tries to use, and in this 5% is sort of divided, maybe 25% for the sender, 75% for the receivers, because there may be many receivers, and this 75% will again in turn be distributed amongst the receivers. So, suppose one sender sending video at a rate of 2 Mbps, then RTCP attempts to limit its traffic, that means RTCP traffic, to 100 kbps. RTCP gives 75% of this rate to receivers, remaining 25% to the sender. Now, we come to another protocol called RTSP. This is real time streaming protocol. That means, when it is, I mean, we have been talking about, let us say, interactive audio or video conferencing, that is interactive live. Now, we are talking about streaming. Now, user interactive control is provided, for example, the public protocol, real time streaming protocol. So, it is a helper application, displays content which is typically requested via web browser, for example, a real player, and typical functions are decompression, if it is compressed audio or video, jitter removal, that means you play them back at a constant rate, error correction, use redundant packets to be used for a reconstruction of original stream, some kind of graphical user interface for user control like rewind, fast forward, etc. So, these are given by RTSP. What it does not do, it does not define how audio or video is encapsulated for streaming over network. It does not restrict how streamed media is transported, whether it is TCP or UDP. It does not specify how the media player buffers audio video. So, these are more at the application layer. So, this is a simple approach for internet I mean streaming audio or video. Audio or video is stored in files transferred as HTTP object, received in entirety at client, then passed to players. So, audio video are not streamed, no pipelining, long delays until play out. So, here the problem is that if it is, let us say, some kind of a movie, and if it is imported, I mean if it is downloaded as that entire file is downloaded. So, that downloading that entire file will take a lot of time. This is of course a very simple approach, and then there is no problem. You download the entire file, then play it any way you like, do fast forward, reverse, any speed, etc., etc. But streaming means as it starts, I mean the streaming, the media as it starts streaming the audio or video file, after some time, after some delay, it starts, the playback starts. So, I mean simple situation is, of course, you have a web browser, web server with audio files, and a media player. So, that is how you do it, nothing to see. So, HTTP request, so browser gets a meta file, then the browser launches a player passing the meta file to the player, and the player contacts the server. The meta file will contain all the necessary information. This is called progressive download. Now, let us look at streaming multimedia client buffering. So, suppose as before, this is the constant bitrate video that is being transmitted. Now, because of the network delay and the variability of the network delay, this is what the profile looks like of how it is received. But if you do this after some sufficient delay and you buffer it, you see the main point is these two are never crossing, these two lines are never crossing. So, now you can play it at a constant rate. So, all this delay variation, etc., that will sort of go, and you would get a nice streaming audio or video. So, this is the basic idea of streaming multimedia. So, this part, the difference between these two, this is the buffered part. So, client side buffering, play out delay compensate for network added delay or delay jitter, etc. Streaming multimedia, where UDP is usually preferred, we will also look at TCP, how TCP is done. So, server sends at rate appropriate for client, oblivious to network congestion. So, often send rate is equal to encoding rate is constant rate, then there is a fill rate for constant rate minus packet loss. So, short play out delay 2 to 5 seconds compensate for the network delay jitter, and so naturally somebody does not really mind so much that if the playback starts after let us say 5 seconds, but this 5 seconds the entire thing will be buffered and that will take care of the jitter, and if error recovery if time permits. TCP, it sends at maximum possible rate under TCP, and fill rate fluctuates due to TCP congestion control, because TCP congestion control, the window size as we have seen can keep on varying. So, larger play out delays smooth TCP delivery rate. So, if you start playing it after quite some time, so that you can handle this TCP variation in rates etc., then it is you can get a smooth this thing. HTTP TCP passes more easily through firewalls rather than UDP. So, RTSP example, meta file is created and communicated to the web browser, browser launches player as we have seen, and player sets up an RTSP control connection, data connection to streaming server. So, web browser gets an HTTP GET and web server presentation description, then the media player it set up a connection with the media server, and it starts getting, it buffers it and starts playing. The media stream comes, you may pause, you may tear down, etc. Finally, I will just mention about two protocols, namely H323, which is an ITU-T standard, which is the old protocol for setting up telephone calls, and we will not go into the details of this. Actually, details H323 is aging a little bit, and there is a newer protocol, namely session initiation protocol. So, this again comes from this thing. So, this is there is a all telephone calls and video conferencing calls takes place over the internet. So, that is the vision. So, you can reach the callee no matter where the callee roams, no matter what IP devices the callee is currently using. So, there is this for this thing for setting up call, there is a large protocol. So, I can just mention it. There are these things for setting up a call, provides mechanism for caller to let callee know she wants to establish a call, then provides mechanism so that caller and callee can agree on media type and encoding, because that has to agree, and provides a mechanism to end the call. Okay. So, the first one is called an invite, and then there are all kinds of commands for this. It also has the facility to determine the current IP address of callee, maps mnemonic identifier to current IP addresses. There are other components of SIP like SIP registers and so on. So, we are not going into the details, and then it has some this thing for call management. That means add new media streams during call, change encoding during call, invite others for a conference, transfer and hold calls, etc. So, there are all kinds of details about codec negotiation, etc. And then you may reject a call also. Okay. So, you see that this part about audio and video and multimedia over the internet is growing very strongly. Okay. At one point of time, network performance was so poor that there was no question of accommodating this, but as the network performance has increased exponentially over the last so many years, now it has become possible to handle a lot of multimedia traffic through the network, and this is becoming more and more popular, and maybe in future of course, as I have forgot to mention one thing, that we talked about INTSERV, we talked about DIFSERV, but the actual strategy that people actually deploy, that when you feel that it is not okay,
put in more bandwidth, throw more bandwidth at it, put another fiber, okay, take up your multiplexer rate, etc., so that you solve the problem, because the demand for multimedia is so great. Thank you.